Assalamualaikum warahmatullahi wabarakatuh. We meet again with the second part of the lecture about the introduction to data acquisition system and about a little bit about the signal processing. So we finish the first part, which is in the signal conditioning elements, which is we try to understand how the signal being converted into a digital signal. Now in this second part, the signal itself is already in digital signal. So now how we want to process it. Basically it will divide into two parts, which is the time domain signal and the frequency domain signal. I will not go detail in terms of the equations involved in this one, but we just want to understand how the process is being done. So I'm going to use the virtual instrumentation software, which is Z.M.Hafizi, to make sure to ease the process of understanding the signal processing, basically the process of digital signal processing. So the time domain signal is actually the signal that have the y-axis, the x-axis is in time. So the signal will move with respect of time. Of course, this is a digital signal. Okay, the time domain, it either first you just display it in real time, or you also can put it in storage. If you can save in storage, you can do two things. First, either you save and then you can view it at a time, or you put in storage, you can do post-processing. Okay, post-processing. Before post-processing, you also can simplify the signal first before you save. I will go in detail about this later, but I will also show the process, how it done by using the Z.M.Hafizi software. So first we need to understand that for the dynamic signal, the signal that we see is in terms of waveform. The wave, either sinusoidal waveform, pulse, random signal, all these are waveform that we see in the display. If you use software, you can see it from the software. If you use, let's say, oscilloscope, it will you can see that one, the waveform in the oscilloscope screen. The waveform analysis, we have a lot of analysis to do to process the signal. First, we can do integration, acceleration, integration. We can use differentiation. I will show this one in the software later on. The band pass filter, we already see the low pass filter in the anti-aliasing. We already understand a little bit on the band pass filter, which is for the low pass. We only allow a low frequency to pass the filter. The same goes to the high pass. It will allow the higher frequency of signal compared to the cut-off frequency. And then band pass is the frequency in between, and stop band is a frequency we only allow the frequency is beyond the cut-off frequency. And we also have a statistical analysis to the waveform, which is RMS, average, getting the average value, maximum value, minimum value, and standard deviation, variance. We also can do arithmetic calculation to the waveform, logic. We can do logic analysis to the waveform. Okay, I will show to you further about the process by using virtual instrumentation. So we've done about the processing about the signal in time domain using this Z.M.Hafizi. Now we see how to convert the signal into a frequency domain. But first we need to understand what is frequency domain. For the time domain So the x-axis is the time. So for the frequency domain, the x-axis is the frequency. So I can show you something like this. So let's say we have one cycle of signal. This is one signal. So we have only one frequency. So if we have the higher frequency, this is higher frequency, so it will move further. That we only get one line, okay, because only one frequency involved. So let's say we have higher frequency than that, so it will be higher value of frequency here. Let's say we combine all these three value in one signal. Oh, sorry, we add one more higher value here. So it will move further in the x-axis. It will move further, showing the higher frequency. Let's say we combine all the signal here. We combine all. So what we get is, in terms of time domain, we can get a combination of signals like that. But in terms of frequency domain, we will show all the signal. See, we have omega 0, 3 omega 0, 5 omega 0, and 7 omega 0. So in software, we can see something like this. Okay, so this is actually a volt, this is a frequency. All right, so we will see further in the DesiLab software after this. But first, we need to understand that the conversion process involve the mathematical calculation analysis. But don't worry, I will not go in detail about this. Just for your own knowledge, this is the equation that we use. Now, the process, the conversion, after the conversion from the time domain to the frequency domain, then we can do a spectrum analysis. There is a lot of spectrum analysis. For example, we have forward FFT, inverse FFT, waterfall spectrum, color intensity waterfall spectrum, transfer function, coherence, auto power spectrum, cross power spectrum. With the advancement of the software nowadays, we just only need to just either we just write the program, or for the case of DesiLab, we just connect the modules to make sure that the signal will do all these analysis. Again, I will show with the DesiLab after this. But before we go further to the analysis, the FFT analysis, or to the frequency domain analysis, we must understand how the process is being done. From time domain, it will cut the time domain into a few blocks. The block that we're talking about is actually a block size. It's according to the block size. By default, the DesiLab will divide the signal in term of block. Okay, blocks. It depend on the block size that we set. So the frequency domain, or the frequency analysis, or for this case FFT, it will use windowing. The windowing is depend on the block size. So why we need to do windowing? Because of the leakage. Okay. Let's say we have something like this. So if we cut the signal, say we set to cut the signal, so look at the first cut here. Look at this unfinished signal. It's hanging. It's hanging. So this hanging, if we convert into frequency domain analysis, it will show incorrect representation of the signal. Right. So to avoid this, because we cut it every time, we cut the signal every time. So to avoid this, we make sure that the area that we cut is being squeezed down. For example, this one. So if we squeeze that one down, there's no more hanging part as stated here. Alright, so the window, it will force the end and the starting point to be 0. That is the function of the window. But of course, if the window function, of course we need to select a proper window function to make sure that we have correct representation of the signal. Because we have a lot of window function, is a mathematical is a algorithm made by the expert in signal processing. So we have 3 example of window function. We have Henning, we have flat top, we have rectangular. Later on in Daisy Lab, I will show you the difference between all these window function. In the figure we see the Henning, it will give a very sharp value of the frequency. I will show you in general. So let's say we have something like this. So we have, this is a G of frequency and this is a voltage. So this area here, now this one. So for the flat top, it will show you a flat signal. For the Henning, it will show sharp top. So this is another comparison between 2 windowing function. So for the Henning, you can see that it's more sharp. Okay, for the flat top, it will give a flat top, but this difference, it depends on pro and cons. For the Henning, it gives the narrow shape, but the maximum amplitude error is 60%. But it will give you a very sharp value. So that's mean in terms of frequency. So for the sharp value, it will give a very nice value here, very nice value here, very nice value here. For the frequency, it's good. But for the flat top, it gives you a broader shape of the top. That's mean we don't know. We have a range of frequency. So we have a lot of uncertainty in terms of frequency. But it will give the value for amplitude with the error of 1%. So it have pro and con. If we want to focus on the signal that we want to indicate the frequency, so we choose the Henning, so it will give us a very nice frequency. But if you want to focus on the amplitude, we go for the flat top, because it will give a very low error in terms of amplitude. So before we finish our topic about the signal processing, I want to show about the real-time measurement. So like I said just now, what we do is when we show the frequency analysis, we cut the signal. We cut the signal according to block size. With a proper cut, we can show the real time of the frequency output. So it will reduce the delay. So let's say for the first block, say if you see the figure there, for the first block, so if we have delay in here, so first block, after first block, it will calculate the FFT for the first block, and then second block appear here, and then after that it will show the FFT for the second block. Same goes with the third block. It will have a delay, and then it will show the FFT. So this is not a real time, because it will show the time domain first, and then it will show the frequency domain. So by the time it show the second block, at the same time, the first frequency is appear. So it have a delay. So how to make sure it's not delay? So we must make sure that the block for FFT is smaller than the block of the measurement. So again, this one is explained in the Daisy Lab software. To calculate the percentage of overlapping is we we minus the time per block minus the processing time and divide by time per block and times times 100. So we can get the percentage of overlapping. We must make sure that we do not have much overlapping, otherwise it will disturb the signal. We have to make sure that this is optimum. Alright, so with that real-time measurement overlapping, I end up this session for the introduction to the AQ and the instrumentation. So basically, if you know how to combine starting power sensor up to the signal conditioning element, the DAQ, and the software, if you can combine all, you can produce your own system. So for example, let's say we have a touchscreen PC based processor, and then we connect with the DAQ, for this case National Instrument DAQ, and then we have a sensor, we have a, let's say, accelerometer and impact hammer. If we combine all, we can get our own complete system for the measurement. Alright, with that I think I will end up my session, my lectures for my parts in instrumentation and control system. If you get any other questions, make sure you text me in the phone number given there, and also you can email me if you have any questions, if you have any requests, more video explaining about the anything you don't understand about this topic, just let me know. I will make sure that I will make sure you're satisfied with the lecture. Thank you very much. I will end up here. See you in another lecture. Thank you very much. Assalamualaikum and bye.